We have an exciting topic for you today, all about Kubernetes automation and specifically the potential pitfalls that we see organizations running into as they try or move toward automation, and 4 practical ways to avoid these issues. Because there's fantastic benefit in automation, getting rid of manual effort, freeing people up to do other things, optimized infrastructure, but you have to do it right or there are these pitfalls. So we're going to talk about that. Andrew, over to you.
Thanks, Chuck, and thanks everyone for joining. So as Chuck said, the topic is automation. It's automation specific to resource optimization. So I want to be clear about that. We are a resource optimization company and product. We optimize containers, we optimize cloud instances, we optimize AI workloads. Today, we're zooming right in on the Kubernetes resources themselves, and we support Kubernetes on all the different cloud providers. Oracle's not here, but Oracle as well, on-prem, wherever it's running. So we're going to focus on Kubernetes today. I'm not going deep into how the product works or giving a demo. We have other webcasts that we've done and there are recordings that cover that. So if you're interested in how the product actually works at a deeper level or seeing it, we can give that information as well. Let's dive in. So if you were to go into our product, and one of the screens you can see if you navigate to it is an analysis of the Kubernetes resources. And again, I'm not going to explain how this happens or what analysis. There's machine learning underneath this that looks at all the patterns and figures out, is a container too big or too small from a CPU request, memory request, CPU limit, and memory limit perspective. And this is just a little visual telling you that for your whole estate, in this case, the big yellow bar in the CPU request means you've got a lot of containers that are way too big from a CPU perspective. For memory, you've got some that are too big. That's the yellow. The red is too small. The gray doesn't have a value. So there's a mix of problems here. Some things are oversized, some are undersized, some don't have requests at all, which can be a problem. And so this is visual telling us, and a lot of companies look this way. In fact, everybody looks this way, where there's a lot of waste, a lot of yellow. At the same time, there's quite a bit of red that can be causing risks. On the bottom right, you see a little warning symbol. There are memory limits that are too small, causing out of memory kills. And that's kind of the business problem that we solve. We cut the cost of an environment by quite a bit by downsizing things that are too big, but we also upsize things that are too small to stop throttling and out of memory kills. And again, there's other webcasts that cover that in some detail. But the net of it is, what I want to do is identify these opportunities to save or de-risk an environment, and I want to automate them, and I want to fix them on the fly. And overwhelmingly, our customers want to automate them. So that looks like what you see on the right here, and I'll describe that in some more detail. But from an automation perspective, you can't really do this manually. Most customers have a lot of containers. You're not going to go and manually resize them by hand. That's not going to work. We see some customers implementing GitOps approaches. We do have an API, and you can hit our API and get the recommendation and do a pull request and kind of integrate it that way. But that's also quite a bit of work. So what we promote and what we have in our product is a centralized automation controller. It is basically a mutating emission controller. It supports eviction. It supports in-place resizing. So it's kind of one-stop shopping to just make things right. And it has a bunch of advantages in doing it that way. You don't really need to interact with every app owner and open a change ticket. A lot of times in Kubernetes, it's not necessary to do change management around these things. You're just basically bumping the requests and limits up and down. And it has another advantage in that a lot of times, a lot of containers are launched off the same template. And so you're stuck with the same values. But with our automation controller, you can also tailor it so that a certain container that's running in a certain namespace can have its own size distinct from the same container in a different namespace. And on the right, what these graphics are showing, that's just part of, if you were to go into our UI, and we'll tell you at the end how you can actually go do that. The top one is an example of a CPU utilization chart as the blue, with the requests being brought up to be a higher level because it was too low. And the bottom one is an example of some memory requests and limit being brought down. And I'll go into a little more detail in a second on that. But the idea here is that if I do this automatically, what will happen is if you look at this stylized graphic, which is actually, there's a graphic just like this in the product that says, the orange line is what I'm asking for. So in this case, for CPU, I'm asking for a lot of CPU resources. The blue and the gray at the bottom is the utilization, the sustained and peak utilization. And we're simply not using it. And that big yellow bar I showed a minute ago is what causes this. I asked for 5 CPUs, but I'm only using 1 CPU or a tenth of a CPU or whatever the case is. And so that's the big mismatch we find, is that there's a lot of spare capacity that's in the environment because you requested it, but you're not using it. Kubernetes needs to run enough capacity. The autoscaler has to provide enough capacity for all the requests, whether it's used or not. So this can be expensive. You're running low utilization. And so from an automation perspective, once we have all the recommendations that we want to do, we can define an automation policy saying I want to automate these namespaces, these containers in certain ways. I'll talk about that in a minute. When we flip on automation, you'll see that orange line coming down because the system will automatically start changing the container requests to be more in line with actual utilization. And when it starts hugging that curve, then you start getting a lot more efficiency and you start driving the cost down. Now, what happens is it doesn't just come down. You'll start running on fewer nodes. The blue line will actually come up because as I stop requesting so much, I'll run on fewer and fewer nodes. And if you're using Carpenter, it'll automatically consolidate. If you're using scale groups, it should automatically rein them in. And you just end up running on fewer nodes that are better utilization if that orange line, if the request values aren't crazy high. So that's kind of the vision of automation. You come up with the correct answers and you just make them. Now let's get a little more specific into what this actually looks like. So this is an actual automation policy, and I'm not going to read through every line item, but the way it works is you can have multiple policies, and you can basically register a policy to say, in this case, I want to do full optimization on a certain scope, and I can say these namespaces are in or they're not in, or these pod labels are in or not in. So I can say do everything or don't do these namespaces or only do these namespaces. So I can set a scope for an automation policy. And again, you can have multiple ones. So I can say my critical workloads have one policy and my other ones have a different policy. And on the right-hand side is the actual policy from an automation perspective. So there's a different policy that says how we actually come up with requests and limits. It's even more sophisticated than this. I look at 95 days and I look at all the history and I look at the peaks and I figure out, okay, this is what I want my request to be. There's a different policy. Once we have that answer, this policy kicks in and says, okay, what am I going to do? And you can see, this is the full optimization policy, and you can see, am I doing upsizing of CPU requests, downsizing, CPU limits, all these things. It's all down in the body of it, and there's a bunch of really important things I'll come back to and dig into some of these after I go through the pitfalls. So there's a lot of settings here that are pretty important to have really, really fine control over how you automate these things. So again, if you're working with production workloads, you want to make sure that's very, very safe, whatever you're doing to optimize them. So with a policy in place, again, you'll get something that looks like this. You saw this a couple of slides ago as well. This is an example where on the CPU side, we're bumping up the CPU limit a little bit based on recommendation. Probably something that's off screen here. We're looking at a kind of a short view of the data here, but we look at a lot of history, and there's probably some spike in there that says, we need a higher limit or we're going to throttle the workload. The CPU requests was also automatically decreased at the same time. So the orange lines are the requests, the purple lines are the limits. And we're saying we were a bit too high on the request. It doesn't look like much here, but we're cutting it in half, which will cut your spend in half if you do enough of this stuff. So even though it looks like a small delta, it's actually pretty important. On the right-hand side, we're also taking the memory request and bringing it down a bit because it's way higher than the actual memory utilization. And again, so there's a lot of detail underneath this of how this is generated. And again, we can provide some links on how to get that. But this looks pretty straightforward. So I want to make some adjustments to my requests and limits. I just want to do it automatically. What could possibly go wrong? What could go wrong here? And I'll start by saying, of course, if you bring these values way too low, something's going to go wrong. So that's a given that we don't want to bring limits way down to cause throttling or to cause that a memory kill. So I'm not going to talk about that because that's just a given. That's not really an automation problem. That is just don't come up with a dumb answer. So we want to make sure that the answers are rational. We look at a lot of history to say, yep, we're safe to bring that CPU request down. Our nodes are really underutilized. So let's bring them down and get our utilization up. And let's make sure the limits are safe or maybe even not set. I'll talk about that as well. So you can also not set CPU limits, for example. A lot of our customers don't do that. So getting the right answers and not making things too small, of course, is a given that that could cause things to go wrong in a hurry. But supposing I have the perfect answer, I have the best requests and limits possible for a given container, then what can go wrong? So let's start with one of my favorites, HPA conflict. And a lot of people on the call may have heard of this. It's kind of a known issue that it's easy to mess up HPA when doing vertical scaling of workloads. And in fact, VPA messes up HPA. So if I look at, let's just take an example workload here. So this is a memory utilization of a container. And you can see at the bottom, it doesn't quite go down to zero. I should note that the y-axis isn't always centered at zero. So it starts at about 250, 500, 750. And the way you read this is that the blue line is the actual utilization in this period, and it was sitting around between 500 and 700 millicores, or megabytes, sorry, in this case, it's memory. The request was sitting at about 1600. That's the orange line. And the recommendation was that it come down to around, looks like about 800. Of course, if I've lied in the product, I can just click on these lines and get the values. The limit was way up or just over 3,000, and we're saying the limit should come down to about 1,500. You don't need a limit that high for this workload. It barely ever does anything. And this line dropping here is where the automation occurs. So that's the automation controller kicking in and downsizing both the requests and the limits on this object to a pretty sane value. You see the request is still higher than utilization. You can possibly even go a bit deeper. So this seems like a good recommendation. This will probably save some money if I do this and make things run a bit better or a bit safer. But it can, this thing, even though it looks really good, can mess up HPA. So let's talk about that. So HPA, the problem with HPA is it's scaling on a metric, or possibly more than one metric. And if you change the metric that HPA is using, it can mess things up. So here we cut the request in half, roughly. And so that thing looked like it was using just under half of the request. After this change, when that orange line comes down, it's using probably 80 or 90% of the request. So this can cause HPA to scale out and more nodes to run. And we've seen extreme examples of this. Like sometimes you see a workload that's not doing very much and you chop the request by 90%. Well, then HPA all of a sudden will go and run 10 times more of that container. So the key here is that if you mess with the metric that HPA is scaling on, HPA can do some really, really weird things. And we've seen this happen, and this HPA conflict is a fairly well-known thing. It can actually have some interesting knock-on effects. So if I bring it down, let's just say I was running on 5 nodes, I brought this down, now it's running on, not 10 nodes, if it's running 5 replicas and I bring it down and then it scales up to 10 replicas of that same thing, we've seen cases where it hits its max. Maybe the max is 8, and so it can't go to 10. So then each of the individual containers gets busier because you're dispatching workloads to them, and their utilization starts to shoot up as well. So we've seen cases where not only does it expand out uncontrollably, when it does expand out, it hits a limit, and then all the individual containers start getting used higher and higher, and they shoot up past their requests. They could even hit their limits, and it distorts everything. All the measurements become wrong. Anytime you're sitting at your max or your min, you're not getting a natural measurement of what the workload actually is doing to the infrastructure. So that's a kind of a subtle point, but the point here is that if I automate the metric that HPA is using, HPA can go a bit berserk. And so you really want to prevent this is key. And implicit to this, of course, is that our product prevents this. It won't do this, but a lot of things don't prevent this and cause issues, including VPA. One of the big reasons why we don't see people using VPA is because it can mess up HPA. And you would think they would work nicely together, but they don't. So this is kind of point number one. You don't want to do things that makes HPA go crazy, especially if it causes the applications to mess up. And so don't mess with the CPU if CPU is a scaling metric. That's point number one. And again, this one is kind of known, like I said, if this is just, you Google that, you'll get an answer on that right away. So it's key to not cause it to happen. Second one. Now this one's maybe a little less obvious, or maybe not, is that the quota exhaustion. So this problem come up. So let's just take a scenario where we've got the memory utilization of a container. It looks like every day, every 24 hours, it gets busy and goes up to 9 gigabytes and then ramps back down to 7.5 gigabytes and up to 9 again. That's the blue line. And we're saying, okay, we should really bring the request up to protect that processing. So we're sure to have the resources when that's happening. We're also saying bring the limit up. Again, you'll notice that this is not going down to 0. So it's going between 7 and 9 gig. And we're saying the limit should be 50% higher than the peak. So that's why we're suggesting bringing the limit up. So again, a pretty rational recommendation. What could go wrong here? Well, quotas. So if there are quotas, you can have quotas on the total requests and limits in a namespace. This is what they look like at the bottom right. So if these quotas are set, then upsizing things can start to cause risk. Downsizing is safe. So ironically, downsizing is the big risk if you don't want to make resources too small. So we avoid that by having smart answers. But downsizing is easier from a quota perspective because it won't hurt your quotas. It actually helps your quotas. Downsizing can also mess up HPA, by the way. HPA can get messed up in either direction, depending on what you're doing. But for downsizing or for upsizing, quotas can be exhausted. If you exhaust your quota, the container won't start. So you can create a pretty serious problem here where your app doesn't run anymore because you're out of quota. So this needs to be avoided at all costs. Now, the subtle thing here is that your container might start, but something else might get affected. The classic example here is that if I have a replica set that's low during the overnight hours and then replicates up to, say, a couple of hundred containers midday, I might be fine for the first half of the scaling, and then I run out of quota. It's tricky. You might not even see there's a problem. You might say I'm going to increase the size of this container and it works just fine and the container starts, but then later it doesn't because the aggregate quota gets messed up. So it's important to take this into account. You don't want to be automating or downsizing or upsizing things if it's going to exhaust your quota. Or the little trick there is also maybe go downsize some stuff first. So there's techniques in here. We do prescribe an order of operation of things to be done when optimizing. So sometimes it makes more sense to upsize first to de-risk. Sometimes it makes more sense to downsize first to free up quota so that you have enough space to then upsize other things. A lot of environments we see, they're wrong in both directions. They're too big and too small. And so you can make a lot of difference by doing things in the right order. So that was point number 2, quota exhaustion. HPA can get messed up, quotas can get messed up. Third one we want to talk about is limit ranges. And I think this is the same example. I'm just going to focus on the limits this time, where I'm bumping up the limit, which seems like a pretty rational thing to do. But if I shrink that up, you can define limit ranges on individual containers. And if the container is outside a limit, then it can't start. Here's what a limit range looks like. Limit ranges can be complicated. There can be multiple ranges, but here you see the max memory is 12 gig. You see the curve at the top. We were at 12 gig and we're bumping it up to 13.5 gig. And the min is 500 meg. So this thing actually isn't going to restart if we try and do this. So of course, now the above example did work because it was checked for. And that's the point here, is that checking for that to make sure that when you're going to resize something, you're not going offside from a limit range perspective is critical. Otherwise, the thing just won't come back up. You can have multiple limit ranges that apply to a single container. These things also define defaults, so they can be pretty tricky. You have to run the whole gauntlet of limit ranges to make sure that the thing you're doing is going to work. Then once you've done that and validated that you're going to be okay, go ahead and automate the change, and the app will keep running just fine. So again, they're different than quotas. It's not an aggregate. It's not adding up. You don't add up all the different ones. It just applies to individual containers. You just can't go outside your limit. And so avoiding this at all costs is also very important. So that's limit ranges. The last thing I want to mention is kind of similar but kind of different. It's the node sizes. So a similar thing will happen. Let's just say I have an example where I'm bumping up my request and my limit in memory in this case again, and I'm increasing the request up to over 5 gig of memory. Now, let's just say for argument's sake, my nodes only have 4 gig of memory. So this isn't going to work out well either. And we've seen this happen at the environments, and if customers have been using products that don't check for this type of thing, they can increase the size and then all the things unschedulable. So I know 4 gigs, I'm just using as an example, would be a pretty small node size, but let's just say for argument's sake, I have a 4 gig node. The limit's okay to go above the node size. It doesn't check that with scheduling, but it will check the request, and you'll need a big enough node. So increasing the request beyond the allocatable resources of the node will make it unschedulable. I say any node because it depends on the autoscaler. So if you're in Carpenter, you might have some really big nodes in your repertoire that you can bring to bear, and it will start one of those and you'll run on it. It may not be ideal because you're spending a lot of money for these big nodes, but it might work. Or it might not. If your Carpenter spec doesn't have anything bigger than 4 gig in this case, then you're not going to start. Scale groups work a bit differently. We see customers running on scale groups or ASGs in Azure or MIGs, and sometimes those can have, or a lot of times those will have a fixed node configuration. You're scaling in and out with a 4-way or an 8-way or whatever node type. That can happen in that case quite a bit because there is no bigger node to get. You can run more nodes, but they're all the same size. So if you resize something bigger than the biggest node, and we've seen, oddly enough, Prometheus being a culprit of this because it usually gets a really huge memory footprint. If you're looking at the total memory and not just the working set, it can be using up almost an entire node. And if you say, oh, it needs more memory, you can easily make it bigger than the nodes, and then it won't start again. So we've seen that happen in action. Again, not with our product because we check for this, and we won't upsize something if it makes it bigger than the node. So again, very important to prevent this or the thing won't restart. So again, these are specific to, even if I have the best possible answer for something as far as the ideal request and limit for a given workload based on the analytics, there are things that need to be checked when you go to do it. Some of them are dynamic to make sure that you can actually make the change and the app will keep running. So again, all of these are things that we've seen happen in the field that we built into our product, our automation controller, ways to prevent it so it won't happen. So those are the 4 main things. I want to cover some other considerations very quickly. As I mentioned earlier, it's important to have really granular policy control Do I upsize and downsize memory limits? We usually like people to start by not downsizing limits at all. Don't bother. Just upsize them if they need to be bigger. It's still safer. But this one I've highlighted is interesting because we can also set things that don't have values, which is quite important. You might want to make sure you have memory limits on everything. Or we can unset things that are set. And that's a case, a very specialized case where a lot of our customers don't like CPU limits. They actually mess things up. I did a podcast on this where my guest got into a lot of detail on why CPU limits are bad. We can probably link to that because it's fascinating to listen to the reasons. So we do see customers saying, I don't care, unset the CPU limits if they're set. You can only do this if there's no quota set on them. So that has to be checked as well. But we can unset things for customers that don't want CPU limits. So that's a specialized thing that we see coming up more and more. Just don't put CPU limits on the objects. We need control over the evictions and dry runs and all that kind of stuff. So you see here, we can enable pod eviction. So you can just wait for the thing to restart and it'll mutate, or you can actively evict things and restart them within the pod disruption budget to make the optimization happen faster. And that's usually desired because you don't want to wait a year to save money. So there's all kinds of settings in here. There's settings for the eviction, there's settings for throttling, that kind of stuff to make sure that you're doing it in a very safe way. And some other advanced things, like I want to make sure I leave headroom in my quota, or I want to use in-place resizing, which is very important. The policy, it's important to have a lot of control, and this might be the policy for a production workload, which is different than a dev workload or a staging workload. And so I can set multiple policies and make sure they automate exactly the way I want them to in a safe and efficient way. Now, in-place resizing is a topic on its own. We support in-place resizing. It's new in 1.3.3, so it's out there in the providers. It's the perfect complement to the mutating controller, so we can change things as they start, or we can change things when they're already running. And between the two of them, you can actually do some really nice automation scenarios. It will fall back on certain things, so you can make it try in place. Nope, it's not possible. I'm not allowed to downsize the limit in place, so it can then try and restart the container. And if that's not possible, it can evict and restart the whole pod, which might put on a different node. So we have a very intelligent fallback to walk through the combination of strategies to automate something. And again, if you can do it in place, that's great. It's really great technology because it doesn't disrupt, but we also kind of use that to complement the mutating controller and the other strategies that we have. Last one, but not least, is audit trail. And it's important to say what you did. And you see on the right here, that's a screen in our UI that says what automation has occurred and when it occurred and what it did. And you can see that graphical depiction of what's going on at the bottom that I showed earlier. And you'll see it's doing things over and over because the pod's restarting and it's re-maintaining the optimization. So you'll see it's doing the same mutation over and over because the pod is restarting. We need to make sure it stays optimal. So full audit trail of that, indicating why it happened, why it didn't happen. All that stuff is important so you can know what's happening and why things are being automated. So I can just go quick here because we're a couple of minutes left. So summary, how to avoid the four main things: avoid HPA conflict, avoid quota exhaustion, avoid hitting the limit ranges, and avoid making a container bigger than the biggest node. If you do that, then you should have very safe, and combine that with the right answers, the actual optimal values, you should have a very safe automation strategy. Again, using granular policy control, in-place resizing, having an audit trail, all these are important aspects of successfully automating resource optimization in a Kubernetes environment. Now, I'm going quickly here. Last but not least, what I was showing you is available online. We have a sandbox. You can go into our website or follow the link in this QR code, and you can go in and click around with demo data, which is where all those screens I used came from. You'll be able to find all the things I showed right there and try them out live. You can also stand up a free trial. It's free for 30 days. So if you want to try it against your data, not demo data, then you can do that as well and see the same stuff happening in your environment and try out the automation and verify that it works. So sandbox and free trial, all available through these links. And I'm sure we'll follow up these links as well in an email. And Chuck, will have 30 seconds.
Thank you, Andrew. If you're heading to KubeCon in Atlanta, we will be there. This is what our booth will look like. If you want to track us down, we will be showcasing some really new and exciting AI-driven access and interface with the technology that Andrew was just showing. Some great innovations there make it easier for users to get to answers quickly and understand the reasons for certain recommendations, as well as some capabilities around optimizing GPU and AI workloads themselves. So the same kind of analytics applied to the challenge of the cost of that kind of infrastructure. So we look forward to seeing you there if you're making that trip. Appreciate everyone joining today. And please do check out that sandbox or submit for a trial if you have an infrastructure that you'd like to analyze through these methods. Thank you, Andrew. Great content as usual. Great detail.
Thanks all.
All right, bye-bye.